Thermodynamics is the physical science that deals with relations between heat. Notice how when you take a warm bath, you get warmer while the water surrounding you cools down. In addition, take a look at this iceberg. It's melting in response to its environment. These all show properties of thermodynamics where there is a direct relationship between heat and molecule movement. At a certain point, the point of interest and its environment will reach a point called thermal equilibrium where the temperatures are the same. Let me introduce you to this equation, Q equals mc delta T. Q is heat, m is the mass of an object, C is the specific heat capacity, and delta T is the change in temperature, or final minus initial. This equation helps you find the required energy to raise or lower a substance to a certain temperature. What is specific heat capacity? It is the required heat to raise 1 gram of something up 1 degree Celsius. Let's try two examples. First, we have 10 grams of water starting at 10 degrees Celsius and increasing to 40. The specific heat capacity of water is 4.186 joules per gram. How much energy is required in this increase in temperature? We find delta T by subtracting 40 by 10, and the mass and the specific heat capacity are given. Plugging the information in, and we get that Q is 1255.8. Now for the second question. We have a starting temperature of negative 20 and a final temperature of 30 degrees Celsius. The mass of water is 20 grams. We just plug in T as 30 minus negative 20 and M as 20, right? Unfortunately, it's a bit more complicated, and I'll explain phase changes because at negative 20 degrees Celsius, water is in an ice form, while at 30 degrees Celsius, water is in a liquid form. Here we have a very important line. This line represents the phase change of water starting as an ice and ending as a vapor. The x-axis represents heat, while the y-axis represents temperature. The red lines represent heating up and can be shown by Q equals mc delta T, while the blue lines represent a phase change, and the amount of heat is found using the equations Q equals m times latent heat of fusion and Q equals m times latent heat of vaporizing. Notice how the red lines halt for a period of time. That's because it takes more time to heat to vaporize or melt than to heat up water. This is supported in our equation because there's no T, meaning that during the phase change, the temperature stays the same. Now knowing this, let's answer a second question from earlier. There are three parts to this. First, from negative 20 to 0 degrees, second, melting, and third, from 0 to 30 degrees. We set up the three equations individually and add up the total Q and get 10,866. Notice how melting required the most heat. This proves that melting takes more heat than heating up. Now let's talk about enthalpy, or the total heat of a system. We can find the enthalpy change in a reaction using the equation delta H reaction equals standard enthalpy of the sum of all products subtracted from enthalpy of the sum of all reactants. For example, we have this reaction here and we are told to find the total enthalpy change. Using the chart online, you can find each molecule's enthalpy represented by kilojoules over mole. Knowing that you have 4H2O and the enthalpy is negative 241.82 for one molecule, you know that the total enthalpy is 4 times that. Do the same to all four in the reaction, and after some algebra, you get negative 1275.9 as the enthalpy change. You might be wondering, why is the change negative? That's because this reaction is an exothermic reaction. Energy is being released. This relates to the first semester when we learned about combustion. In a combustion reaction, a lot of heat is being released, known as an exothermic reaction. Aside from enthalpy, there's also entropy, or disorder. When a solid goes to a liquid or to a gas, there's an increase in entropy, where the molecules are speeding up, aka chaos. Enthalpy, delta H, and entropy, delta S, are related in Gibbs free energy. Delta G equals delta H minus T times delta S. Now substituting the known variables, we create this chart showing that when H is negative and S is positive, a reaction will always happen. When H is positive and S is negative, a reaction will never happen, and sometimes to the other two. Like when we learn about gravitational potential energy in the first semester, there's also potential energy in thermodynamics. Potential energy increases when bonds are broken and decreases when new bonds form. When the increase is greater than a decrease, it's endothermic, and when a decrease is greater than the increase, it's exothermic. Now, how do our labs relate to the first law of thermodynamics? According to the first law of thermodynamics, the total energy of an isolated system remains constant. Energy can neither be created or destroyed. Rather, it transforms from one form to another. Sounds similar to the law of conservation of mass we learned in semester 1. This is represented in our first lab in which we heated water with an immersion heater. The lab provided some inconsistencies because it was not in an isolated environment. The energy escaped the beaker and proved that energy is being transferred and not lost.